Hey everybody, so this is planning experiment 1, and since a lot of teachers may not have covered such experiments, I want to cover them to ensure that if they were ever to come in question number 4, which is the planning experiment, you are Gucci with it, right? So the first experiment that I want to do is to find the percentage of oxygen in air, right? Now, how do we find the percentage of oxygen in the air? There are multiple ways to do that. Multiple different experiments can be carried out, but I'm going to carry out, I'll carry out all 3 experiments for you, but I want to segregate them, right? So we're gonna first cover the first experiment, then the second, then the third, right? So there are multiple experiments, but we'll cover the 3 experiments that are given in your books and whatnot, especially in Pearson, Edexcel, and even in IGCSE books, right? And even sometimes in O-level books. Okay, so how do you find the percentage of oxygen in air? That's a very good question, and in order to understand that, we perform this particular experiment in order to actually calculate, because we already know that you have 78% nitrogen in the air, you have 21% oxygen in the air, and then 1% is carbon dioxide and other noble gases, right? Like argon, etc., right? Out of this 1%, 0.9% is of argon. Argon has the highest percentage of any noble gas in air, right? So that's the composition of your clean, dry air. The reason why I'm saying dry is because air can also have moisture in it, right? Then it's not going to be called dry air. But let's suppose I want to find out that how did we come across this knowledge? How did we know that there's 21% oxygen in the air? So that's the first experiment. The first experiment revolves around the concept that, you could actually have copper right here. He's shown you that there are silica tube packed with copper fillings. So you could have copper right here, and when you heat copper, and you know that in the air you have oxygen. So when you heat copper is going to react with the oxygen in the air, and what's going to happen is this beautiful experiment is going to take place. So copper will react with oxygen in the air to give you copper oxide, right? So that's the entire thought process behind it, that you know that copper will react with oxygen. And because I know that copper will react with oxygen, the volume of oxygen in the air is gonna obviously reduce, right? It's gonna decrease. And why would it decrease? It would decrease because the oxygen is gonna react with copper. It's gonna be used up. When you heat copper, it's gonna react with oxygen. It's gonna form a black solid called copper oxide, right? And you'll realize that you set up this particular experiment, and I'm going to go through it, but I want you to understand the thought process that once all the oxygen reacts, there's going to be no more change in the volume of air. You're going to push this inwards, the copper is going to be heated, and the oxygen is going to react, and at the end of the day, you'll realize that you're only going to have 78 centimeter cube of air left. That means that 79 centimeter cube of air left. That means that that 21 centimeter cube was of oxygen. So if you calculate the percentage of this, you'll realize that 21% of air air is actually oxygen gas. Right now, how do we go about this experiment? Let's talk about it. Basically, again I want to repeat the idea that out of the 100 centimeter cube of air, the volume of oxygen, the amount of oxygen that you have, the oxygen particles, they're going to come into contact with copper particles, they're going to react, and the volume of air is going to reduce. Why would it decrease? Because the oxygen will be used up, and then you're just going to take the initial volume that you had, which is obviously 100 centimeter cube, right? And then you're going to take the final volume of air that you get. What's the final volume of air that I'm going to end up with? Well, through experiment, you'll realize that the final volume of air is going to be 79%. And the reason for that is going to be 79%, no, actually 79 centimeter cube, right? And the reason for that would be because out of this 100 centimeter cube, 21 cm cube of oxygen would actually react with copper. And that's why you need to make sure that you take copper in excess, because if copper is not in excess, what's going to happen is that not all of the oxygen will react. So you're going to get an incorrect reading. You're going to get an understated reading, right? So you need to make sure that even after there's no change in the volume of air, there are some pink solid left behind, or brown solid, because copper is a pink solid. Pure copper is a pink solid, or you could even say it's a brown solid. Mostly it's pink, right? So what I'm going to do is I'm going to take the initial volume, and then I'm going to take, obviously that's the final volume, and I'll subtract the two. So how do you go about it? I'll say, hey, final volume, or Actually initial is greater, right? So I'll take the 100 centimeter cube, that's the initial volume, minus 79 centimeter cube, that's the volume which was left, and 21 cm cube is the volume of oxygen that was actually used up, right? So that's the volume of oxygen, and then in the end you'll just calculate the percentage. Percentage क्या है? 21 cm cube of oxygen was used up, and total air that I had was 100 cm cube, and then multiply it with 100%. So 100 cancels out, you realize cm cube cancels out with cm cube, 100 and 100 cancels out, and you realize that you're going to end up with 21% of O2. And that's how scientists figured out how much oxygen there actually was in the air through this simple experiment. Now, if I want you to write the steps, that's the thought process. But if I want you to write the steps, it's pretty easy. What am I going to do? I'll first, make sure I'll first push the plunger inwards. I'll take these two gas syringes and I'll connect them through this connector right here. That's the silica tube that's with me, and it has some copper fillings with it, right? So what I'm doing actually is, firstly, before heating it with a Bunsen burner, I'll firstly push the plunger inwards. I've actually pushed the right plunger inwards, right? So once you push the right plunger inwards, you realize that you have a certain volume of air, right? Initially, that's 100 cm cube. So the first thing I do is, because both plungers would be outwards, right? So you have to push one inside so that all the air is, accumulated at one end. So I'll say, hey, first of all, the plunger on one side is pushed inwards, right? To just measure the initial volume that I have, it's going to be pushed inwards, all the way inwards, right? And the left hand side gas syringe would give me a reading of, in this case, it's going to give me a reading of 100 cm cube, just for simplicity's sake, right? Done. And then you start to heat up this silica tube right here. You start to heat up the silica tube. Silica tube is basically silicon 4 oxide, right? It can withstand SiO2. It can withstand, this tube can withstand the heat of the Bunsen burner, so it's not going to melt anytime soon. So you're going to start heating it with a roaring blue flame of the Bunsen burner, right? So heat the tube, because in order for oxygen to properly react with copper, you need to heat it, right, and form the black solid copper 2 oxide. So heat the tube with roaring blue flame, a blue flame of the BB, of the Bunsen burner. Done, sir. And then what do you want to do? Once you start heating this up, you're going to push the plunger inwards so that the oxygen starts to react with this copper right here, the equation that I showed you at the start, right? So the oxygen is going to react with copper, and the one that the amount of air that did not react is going to go to the right side, and then you'll push the right side again, and then the left side again, and the right side and the left side. You'll continue to do this until all the oxygen, until there's no more change in the volume of air, right? So once you push this inwards towards the right, you're going to have a lower volume because some of the oxygen may react, but maybe not all reacted. So you're going to push this inwards again so that the volume of oxygen that was left behind also reacts. And then you push inwards again and again and again and again till the volume of air becomes constant. And that's going to be literally 79 cm cube, which will be left behind if you perform the entire experiment accurately, right? And you'd realize that one thing you also need to do is that you need to continuously heat it, but you're going to pick up the Bunsen burner and you're going to move it along the silica tube in order to make sure that all of the copper starts to react, or all of the copper is hot enough to react with this air right here. And make sure that when the oxygen, the volume of the air, when the volume of the air is no longer changing, you need to make sure that there are some pink solids left behind. If there isn't any pink solid left behind, it's just a black solid, and the volume of air is no longer changing, that means that maybe the copper that you took was not in excess, right? So maybe the volume that you get might even be 81 cm cube, right? Or 82 cm cube, because you did not take copper in excess. So you need to take a lot of copper filings. Why? Because I need to make sure that all of the oxygen reacts. That's actually like a precaution, right? And always use, wear gloves and wear eye protection. And, you need to heat carefully, wear eye protection. And yeah, that's pretty much this. Yeah. That's that. Khair. Acha ji. So now I've completed the entire experiment for you, and I'll just quickly go over the points. So after you heat the tube with the roaring blue flame of the Bunsen burner, you start your experiment. And how do you start your experiment? You start to push the plunger on the left hand side right here. I'll show it to you. On the left hand side, you start to push the plunger inwards so that the oxygen in the air starts to react with the heated copper, right? And once it starts to react, some of it would react and some of it would go to the right hand side, right? And then you're going to push the right hand side plunger again in order for the unreacted oxygen to further react with the copper, and then it's going to come to the right hand side, right? So I've written it for you. The plunger in the left hand side is at the left hand side, or in the left hand, you could fix the English for it, but the plunger at the left hand side is pushed inwards to pass the air over the hot copper. And we know that once the air is pushed over the hot copper, this reaction is going to take place. The copper is going to react with oxygen, and it's going to give you copper oxide, which is a black solid. So a black solid would start to form, right? And you need to understand that the black solid, you're heating it at one point right here, and that's not right. You're not going to just heat it at one point, because the black solid is then going to form here, and you would not have, all the other copper would not be heated enough to react with the oxygen. So you need to make sure that you actually take the Bunsen burner and you take it along this silica tube. You use the Bunsen burner along the silica tube, so every time it heats up fresh copper, right, in order for it to react with the unreacted oxygen. And that's what I've written here. So as the copper reacts, the Bunsen burner is moved along the tube. Why is it moved along the tube? So that it's always heating more and more fresh copper, because once copper oxide forms, it's no longer going to react with oxygen, because the copper has reacted with oxygen to form copper oxide. The oxide has already formed. And then you continue to do this sequentially, left to right, right to left, left to right, right to left. Just make sure to not push it so much that the plunger pops out of the other hand side, right? So you're going to continue to do this sequentially until there's no more change in the volume, and then you allow the apparatus to cool down at a room temperature and pressure before taking the final reading. And the reason for that is it's pretty simple, because from your physics that gases expand when they're heated, right? Because once you heat it, and from chemistry you also know that once you heat gases, the kinetic energy of gas particles increase, and they obviously move quicker and faster and further apart from each other. So gases actually expands when you heat them. So taking the reading without letting it cool would not be the correct reading. It would be an overstated reading. So you need to let it cool for it to come back to its to its original volume, which is actually the volume that will be left behind. So that's why you need to let it cool, because gases, they expand when they are heated, right? So you need to let it cool so that they come closer together. The particles of gas once again come closer together to their original position. And then you'll realize that once you let it cool and you take the final reading, it'll be 79 cm cube, and the starting reading was 100 cm cube. Why would the final reading be 79 cm cube? Because you know that out of 79, 21 cm cube of oxygen was used up, and that's through an experiment. Scientists used this experiment and they figured out, okay, 79 cm cube is left behind. That means that the 21 cm cube was the volume of, this was actually the volume of oxygen that was consumed. That's the volume of oxygen in 100 cm cube of air, right? So you'll realize that if I want to calculate the percentage, that's going to be 21 cm cube. That's the volume of oxygen over the total volume into 100%. Obviously cm cube cancels out, 100 cancels out with 100, and you get 21%. That's how scientists figured out how that's how they figured out the volume of oxygen in the air. So that's one way they figured it out, right? That's one way you could jot down this experiment for you. But remember, the idea behind the planning experiments is to first read the question carefully, and then you start to absorb the question in a way to develop a thought process. So always develop a thought process. All these nitty-gritty details you could write if you had developed this thought process at the beginning of the class. Now, a question that could be asked in this particular experiment, maybe if it's tested in the ATP, maybe if it's tested as another question or whatnot, so, the examiner may ask this question that, okay, now that you know all of this, I'll test a theoretical question from you. What if at the end of the reaction, you were left with 60 cm cube of air? Let's suppose, right? That's just a question from my side. just to understand that, just to see whether you've understood the concept, right? So what if at the end of the entire experiment, when the volume of gas was no longer changing, you had 60 cm cube of air? If you have this information, I want you to figure out what was the starting volume. Pause the video for a moment and try to figure it out, and then play it, and you would realize that whether your answer is correct or not. Okay, so now you'll realize that at the end, if I have 60 cm cube of air, what is the percentage of this? Well, I know that 21% of oxygen must have been consumed, right? Because all the experiment is done correctly. So if I am ending up with 60 cm cube of air, that means that out of this 60 cm cube of air, 21% has been used up. So effectively, this 60 cm cube of air is only 79%. So if I were to figure out, okay, hey, what about the 100%? What about the 100%? How much air did I have at the start? That's the 100%, right? So that's x. Cross multiply, what do you get? It's simple mathematics. X equals 60 times 100 divided by 79. Because realize that at the end, when I'm ending up with 60 cm cube of air, I know that, so that's only 79%. 21% was consumed. So I want to figure out that if 21% wasn't consumed at the start, if I had 100%, what would have been the volume of air? So it's simple mathematics. X times 79, 60 times 100, and 79 is being multiplied, so divide 79 on both sides. You're going to end up with what? X equals 60 multiplied by 100 divided by 79. You're going to get 75.9 cm cube of air. That's what you started off with. And my question to you guys would be, how much oxygen was consumed? How much? The percentage is 21%, but how much O2 is consumed? You started off with 75.9 and you ended up with 60. So if you take the differential, you'd realize that 15.9 cm cube of oxygen has been consumed, and realize that this 15.9 cm cube is exactly 21% of this beauty right here, of the total, right? So that's one way of figuring out the percentage of oxygen in air. Now, experiment 2, if I talk about experiment 2 of finding the percentage of oxygen in the air, that's by using the concept of rusting, right? So there are actually two experiments. In experiment 2, you could have two subparts. One is A part and one is B part. They're two different experiments. Now, the rusting of iron, obviously, to calculate the percentage of oxygen in the air. That's the second experiment. Now, I'll first talk about the A part, where I'm going to use iron wool. Right? I'm going to use iron wool. You could search up how it looks, but that's iron wool that I'm going to use. Right now, what is iron wool? It's basically iron, obviously, but what you do is you make a setup like so. I'll tell you how you make it. So I'm going to have a beaker right here. And I'm going to have a test tube right here, and I will tip that test tube to the side. After here I'll place iron wool inside this test tube. So let's suppose that's my iron wool. Iron is obviously Fe, right? So iron wool मैंने इसमें डाल दिया. I've put iron wool in this test tube, and now I'm gonna tip the test tube to the side a little, like so. Don't mind my drawing, but hey, that's how it is. And this beaker actually contains water, right? Because you want to rust iron, and you know that rusting of iron needs two things. It needs oxygen and it also needs water, right? So now if I've taken my test tube right here and I've tipped it to the side inside water, you also have iron. Now before I do this, I will also measure the length right here. I'll measure the length of the test tube at the beginning, right? What is the length of test tube? Because that's how much air there is at the start, right? So that's the length of the test tube that I'm going to measure initially. Let's suppose that's 10 cm. Right? Now, what I'm going to do is, once I've placed it inside water, what's going to happen is that because you had air inside the test tube, air is all around us, but you had air inside the test tube, and I measured that to be 10 cm cube. This bit right here, I measured this bit right here to be 10 cm, sorry, not cm cube, 10 cm length. That's what I measured with a ruler or whatnot. So once I measured this, I placed it inside the beaker containing water, and what's going to happen is that the water would start to displace the oxygen that's being used up. What's going to happen is that because you have iron here, you've also exposed it to water, and there's oxygen also. And remember, the iron wool that you take, it's like wet, the iron wool that you take, it's wet initially. You just sprinkle a little water, some water molecules on it, in order to make sure that the iron becomes wet, so that once it comes into contact with oxygen, it starts to rust. So the iron wool would be wet, and the assumption that we take here is that, okay, the volume of water is almost negligible, right? We don't take the volume of water. We just say, hey, that's almost negligible, because you just sprinkle a few drops to make the iron wool wet, right? In order for it to react with oxygen and obviously rust. So what's going to happen is, once the oxygen starts to come into contact with the wet iron wool, the rusting is going to start to take place, and the oxygen inside this test tube which was present is going to be used up. And once the oxygen starts to be used up, a vacuum will be created, and the water is going to go inside the test tube, inside the test tube. And at the end, it takes about, this is a very slow reaction, it takes about a week. So once you perform this experiment totally, at the end, when you take out your test tube, you're going to realize that you're going to have the rusted iron here. There'll be like a red brown rust here, and there'll also be some water, right? So then you're going to take this reading, this length right here. You're going to take this length, because that'll actually be the final length that you're going to measure. So once I measure this final length, that's around maybe 7.9 cm. And what I'd realize is that initially it was 10 cm, and now it's 7.9 cm, which means there's a decrease of 2.1 cm. And why would that decrease be? 10. Why would that decrease be? That decrease would be because of obviously oxygen being used up. This water that has accumulated here is because the oxygen was used up, and that created vacuum for the water to go inside this test tube, right? And why do I tip the test tube? Well, such details are not required by your course, but the reason why you tip the test tube is, if you place it totally vertical, what's going to happen is this may create a seal here. This just may become a sealed a sealed system, and if it becomes a sealed system, it will stop the water from going up, because there's that physics comes into play, because there's atmospheric pressure that will be applied here and whatnot. So water may not be able to travel upside in this test tube if it's totally vertical because of atmospheric pressure. But who cares? Nobody cares about this, right? Khair. So now if I want to write the steps for it, what are the steps? Now that I've understood the thought process, now it's easy for me to write the steps. What am I going to say? I'll say, hey, first of all, take wet iron wool, and then inside a test tube. This literally gives you 2 marks, one for the iron wool, wet iron wool, and then one for test tube. So place it, take wet iron wool inside test tube, and obviously what am I going to do? I will measure the initial length, of the test tube, with iron wool, obviously. Done, sir. With wet iron wool, and that's what I'm doing. Here is the iron, and I'll start here. I'll start measuring from here. It's a-okay, but I don't want to go into the complexities of measurement. So it's a-okay to start from where the iron wool is present. So let's suppose this was the iron wool right here. So I'll measure this, and let's suppose that's 10 cm, right? That's 10 cm, and which is, I'm gonna also write the reading, that is 10 cm. That's the length. And then I will tip it inside. I will place the test tube. Place the TT, the test tube, inside a beaker containing water. Make sure that the test tube is tipped, right? So tip it to the side. You could say tip it to the side, tip it to the side. The siderino. And once that's done, what am I going to do? I will just wait a week, The water will start to move up the test tube to replace the oxygen that's being consumed. So the water starts to move up the test tube to replace the O2 that's being used up, And then you will measure the final reading. It takes about a week, okay? Measure the final length, you know. And when you measure the final length, you will tell the examiner that, hey, this is the rusted iron, and that's also, you know, some water. So that's water, that's rusted iron, hydrated iron, iron oxide, yeah. So rusted iron, and that's the distance I'm gonna measure now. And let's suppose that's 7.9. Although my drawing is not accurate, but I just want to get the idea across. And then what am I gonna do? I'll say, hey, you just perform calculation, right? So I'm gonna take the initial reading, which was 10 cm, minus the final reading. This is gonna give me the length difference because of the oxygen consumption. If I want to now find out the percentage, it's going to be 2.1. That's the difference divided by the initial reading, which was 10 cm, multiplied by 100%. What does that give me? Cm and cm cuts off, 0 cancels off with 0. 2.1 multiplied by 10, that gives me 21, and put the percentage sign here. So that's the other way of finding the percentage of oxygen in the air. Yeah. Now, I did say that there's a second way of finding the volume of oxygen or the percentage of oxygen in the air through another method. So I'll call this method number A. It's just a difference of apparatus, right? And then I'll call the other method number B, Reno, right? And if I show you the apparatus for method number B, I'll show it to you right here. So that's the apparatus for method number B, right? So it works on the same principle that you take wet iron fillings. So it's basically iron, why am I calling it fillings? It's iron filings, right? So I take wet iron filings, and wet means that there's some water present, right? And we ignore the volume of water. That's what makes this experiment beautiful. That's just an assumption that we take, that the volume that the water actually takes is negligible, is almost negligible, right? And the reason for that is obviously you've sprinkled just a few drops on iron, right? Just to make it wet so that once it comes into contact with oxygen, it rusts, right? Now, my question is that we know that air is all around us. Air is inside the connecting tube. It's also, or you could also call this the delivery tube. So it's inside the connecting tube or the delivery tube, and it's also present inside this container right here, inside the conical flask, and it's also present inside the gas syringe, right? Now, how do you actually calculate how much air is present here, here, and here? Now, one way to do that, normally we just ignore all the air here and we just take into account this air. But one way to do that is to fill up before you put all of this, you just fill up the conical flask with water and you place a bung inside it. You fill it up till here, right here, you know. And once you fill it up till this point, you basically use a marker to mark this, and you're going to say, hey, it has, let's suppose, around 130 cm cube of air, you know. That's how you fill it till here, and then you figure out, okay, and then you just remove all the water from it inside a measuring cylinder, and you put a mark here, and you say, okay, that was 130 cm cube of air. You just measure it, right? And then, normally we just ignore the volume of air here, and we just take into account the volume of air inside the gas syringe, right? So if I show you the entire how it'll work, is that what's going to happen is slowly and gradually, that this is wet iron filings, right? So what's going to happen is that you're going to record the initial reading on the gas syringe. That's what you're going to, this was just fun fact, but what I'm going to actually do is I'll record the volume of gas inside the gas syringe, right? And then, which is obviously my air, right? So I'm going to record the volume of air inside the gas syringe, and I will leave this apparatus for about a week, right? And I'll leave it for about a week, and what you're going to notice is that this plunger is going to move inside on its own. Why? Because you have iron here, you have water here, and it's like wet iron filings, and it's going to come into contact with oxygen, and once it comes into contact with oxygen, obviously it's going to start to rust, it's going to react, it's going to start to rust. So the air, the reading that you have here is going to slowly start to, this plunger is going to slowly start to move inwards, because the oxygen is being used up here. So the volume right here is going to obviously decrease, right? So you will leave it for about a week until the reading on the gas syringe right here no longer changes, right? And you're gonna have something like so. Okay, so what you're gonna do is you're gonna place wet iron fillings into the conical flask like so, and then what you're gonna do is you're gonna record the initial reading on the in the gas syringe, right? That'll be the reading of the amount of air that you have, the volume of air that you have, right? And then what you're gonna do is you're gonna leave the apparatus for about 1 week until the reading on the gas syringe stops, or until the reading on the gas syringe stops to change. So obviously what's going to happen is that the plunger is going to slowly move inwards because the oxygen is going to be used up by the iron, by the wet iron, because obviously rusting is going to take place. So you're going to leave the apparatus for a week until the reading. It's not necessary that it must be a week, but you just need to wait up and hold up. You have to leave it until the reading on the gas syringe stops to change. Usually it takes about a week, right? And then you're just going to record the final reading on the gas syringe. And then what you also need to understand is that the total volume of the entire apparatus is going to be composed of the volume of the conical flask, as well as the volume of the connecting tube, as well as the volume inside as well as the volume inside the gas syringe, right? So it's the volume of air inside the conical flask, inside the gas syringe, and inside the connecting tube, right? The volume of air, right? And what you need to understand here is that the volume, when you take out the initial volume of conical flask, that's 130, and then the air the air inside the gas syringe, that's about 92. That's I've measured it. And this 12 inside the air inside the connecting tube or the delivery tube, this 12 cm cube of air, I've also measured this by putting a lot of water inside and just measuring the volume. But what you'll realize is that this will remain the same, this will remain the same. The only change that you're going to observe is going to be the plunger moving inward. So the only change that you're going to see is going to be the change in volume of the gas syringe, right? But if you take the total volumes, the total volume initially is right here, and that's the final. And if I just take the difference between the two, I'm going to say, hey, you had 234 cm cube of air inside the entire apparatus, and then subtract 185 from it. Obviously, what do I get? I get about 49 cm cube. That's actually practically how it happens. And then you calculate the percentage. So 49 cm cube is obvious. This is obviously the volume of oxygen that's been consumed, right? Or that's been used up. So 49 divided by the initial volume, which is 243. I'm just calculating percentage, right? Multiplied by 100%. So cm cube cuts out. 49 divided by 234 multiplied by 100. That gives me 21%. So that's another technique to find out the volume of oxygen by using rusting of iron. Right now, also realize that since you guys are in IGCSEs, you don't need to worry about these two that much. But if it were to ever come as a precaution, you could write it. But you only just, if you were to plan an experiment, you'd just say, hey, the volume would start to decrease in the gas syringe. The initial volume was maybe 92 and the final is 43. You take out the percentage from that, right? Okay, now one more thing that you need to acknowledge is that sometimes what could happen is that the answer that you get may be less than 21%, and there could be possible reasons for it, right? The first reason could be that the experiment was not left to for a long enough time period, right? Because what would have happened is that not all of the iron would have had the chance to react with oxygen inside the apparatus, right? So maybe you would get a value less than 21% because some of the oxygen may still remain unreacted because you did not leave the experiment for a long enough time period. And then the other reason could be that the iron that you had, the wet iron filings that you had, may not have been in excess, right? So you'll realize, and how do you ensure that it's in excess? How do you ensure that the wet iron filings that you have are in excess? You ensure it by adding, so many iron filings that even when the volume of the gas syringe, even if it's no longer changing, you still have these iron filings available. It's not just red, brown, rusted iron everywhere, right? So one other possible reason could have been that not enough iron was added at the beginning, right? not enough iron filings were added at the beginning of the experiment, right? So you need to understand that iron must also be in excess, that which means that there must be enough iron to react with all of the oxygen present, right? And that's pretty much it about this particular experiment. Now there's also another experiment that you could use to find the percentage of oxygen in the air, and that's using phosphorus, right? I'll quickly go over it. Let me just add the diagram and I'll quickly go over it, and that should do the job. So I've covered all the experiments that can maybe possibly come in the exam for you to calculate the percentage of oxygen in the air, right? So let me just add the diagram. Now the idea, I've added the experiment, the apparatus, but the idea behind the apparatus is that you need a few things beforehand, right? You need to know a few things beforehand. You need to know that phosphorus is a very reactive element and it's gonna react with oxygen, right? In terms of oxygen, it'll react very, very quickly with oxygen, right? And it's gonna react with oxygen to produce an oxide, which is phosphorus oxide. And this phosphorus oxide, fun fact, is a gas, but this gas is also soluble in water, right? So when this phosphorus reacts with oxygen in the air, let's suppose that's the air present, when it reacts with oxygen in the air, what's going to happen is phosphorus oxide forms, but it's going to dissolve in the air, in water, right? And so once oxygen starts to be used up from this empty space right here, which is obviously filled with air, once oxygen is used up, there's going to be a vacuum created and the water level is going to rise up, right? And the phosphorus oxide obviously dissolves, right? So what you're going to do is, the thought process behind it is that I'll mark the initial reading of water level, and that's maybe at 10 cm cube, that's maybe at 10 cm. And then and then what you're going to do is not 10 cm cube, 10 cm, right? I'll just measure this with a ruler and I'll say, hey, that's 10 cm, that's the initial reading, not cube, because it's length. So then what's going to happen is, once the water level rises up, you're going to measure this length right here, right? And once you measure this length, you'll realize that this length is going to be around 12.1 cm, right? Now, why do I know that it's going to be 12.1 cm? Well, I know because I'm Sir Suleiman. But the reason why I know is because once the water level rises, it's going to only rise to the extent of oxygen that's been used up, right? So if I know that you had 100% of air and 21% oxygen has been used up, so this reading will only rise by, this is 10 cm, but it'll only rise by 21%, right? And if you take, if you calculate the percentage, if you say, hey, you have 10 cm and you make it rise by 21%, so 10 cm multiplied by 21%, you end up with 12.1 cm. That's what I know, but that's how scientists actually found out. ये तो अब मुझे पता है ना, but that's how scientists found out the percentage of oxygen in air. So what happens during this experiment is that you have an evaporating basin, that's phosphorus solid placed on top of it, and you have this this bell jar, and that's called a trough. It's like an elongated beaker type, and it's like a wide beaker, but it's called a trough, right? So what's going to happen is that initially what I'm going to do is, I will set up the apparatus as shown right here. I will set up this beautiful apparatus and I will measure the initial level of water on the side of the bell jar with maybe a waterproof pen or maybe even a sticker, right? So I'll write all the points down in a second and then I'll resume this class. Okay, so I've written the points, I've written it in points just for your understanding, that what you're going to do is you're going to set up the apparatus like so. There's this bung at the top. Obviously, you don't want the air to escape because I want to find out the percentage of oxygen, right? So what I'm going to do is I'm going to mark the initial level of water, that's about 10 cm, let's suppose, and I'll mark it with a waterproof pen so that, it does not, the reading does not, just get erased, and the if it's not waterproof, it will dissolve inside water, obviously. So then how will you get your reading? So I'm going to use a waterproof pen or a sticker and whatnot, and what I'll do is then I'll quickly remove this bung, and once I remove this bung, I'll use a hot metal wire right here. What I'll do is I'll remove this bung, use a hot metal wire to ignite phosphorus. Once phosphorus starts to ignite, it's going to react with oxygen to form phosphorus oxides. They're like white steamy fumes, right? They're white steamy fumes, but after some, and once you ignite it, you'll quickly, put the bung back on. You don't want any of the phosphorus oxide to escape or any of the air to escape, right? So once phosphorus oxide reacts, you're going to get the gaseous state of phosphorus oxide, but after a certain while it's going to start to dissolve in water. And obviously once oxygen starts to react with this phosphorus right here, once the oxygen starts to get consumed, there's going to be a vacuum created and the water level would rise to compensate for the oxygen that's been used up, right? So the water level rises right here, right? And you're gonna continue, igniting this phosphorus again and again until the water level stops to rise, right? You're just gonna stop the record. Once the water level stops to rise, you're just gonna hold your you're going to record the final reading there, stop the experiment, record the final reading here, which is now 12.1, right? So I've written the steps here. You mark the initial level of water with a waterproof pen, remove the bung, ignite phosphorus with the help of a metal wire, and put the bung back, and then the water level is going to start to rise inside the bell jar, and then you're just going to mark the final you're going to mark the final reading when the water level stops rising, right? And then you're just going to take out the difference. So initially it was 10 cm and finally it was 12.1. So 12.1 minus 10, that gives me the amount of oxygen that's been used up, because when I take the difference between this 2.1 cm rise, this 2.1 cm rise is because of the oxygen that was used up. So that's due to oxygen. And now it's just simple calculation. So 2.1 divided by the initial reading, which is 10 obviously, multiplied by 100. So 2.1 cm divided by the initial reading, which is 10 cm, multiplied by 100%. Cm cuts out with cm. 2.1 divided by 10 multiplied by 100%, that's 21% of O2. So that was the last way of calculating the percentage of oxygen in the air. Okay, and one more thing that you guys need to know is that it's important that there's still some phosphorus left on the evaporating basin at the end of this experiment, because only then would you be satisfied with yourself, okay, hey, I've used excess phosphorus, right? Because if there's not excess phosphorus, the percentage of oxygen that you may get might be, or not might be, will be lower than 21%, because you wouldn't have enough phosphorus to react with all the oxygen present inside the jar. So not all the oxygen might have been used up. These are precautions which you need to know. And one fun fact as well, you shouldn't perform this experiment because even the teacher who's performing this experiment needs to wear goggles or maybe even a face shield, and also have the room ventilated, because phosphorus oxide obviously is an acidic oxide, so you need to be very, very careful when performing this experiment, right? Okay, that's pretty much that, and see you guys in the next bit. Bye, ciao, bye bye. Okay, I already said bye bye, but because I'm making this video now, I will also recommend Pearson and Edexcel students to watch it. So I'll also give you one more precaution, that once you finish the entire experiment, you use a glass rod to, once you perform this entire experiment, you remove the bung, and after everything is done, you want to now clear up things. So you remove the bung and use a metal wire to push this evaporating basin inside the water to prevent any other phosphorus from to make this wet and prevent it from reacting with oxygen in the air, to prevent it from effectively reigniting. Yeah, that's that.